I'm going to show how I found the general formula for the sequences which have a common ratio between the differences of each consecutive number. Now I know that sounds like a lot, but let's take a look at this sequence to begin with. Now if we take the differences between each term, you can see that each of these have a common ratio of 4. And I wanted to know if we could use this to write a general formula for this sequence using this common ratio between the differences. And I wanted to do this for all sequences, not just this one, which follow this. And to do that, let's take a step back and let's replace each of these terms with a variable. And let's say that the difference between the first two terms is x. And now, in this case, the common ratio between the differences was 4. In this case, let's say that the common ratio between the differences is going to be 3. So if it's 3, it means that this difference will be 3 times the previous difference. So this will be plus x plus 3x plus 9x. And now from here, what I want to do is I want to write all of these terms in terms of the first term. So it will look like a0 plus x, a0 plus 4x, and a0 plus 13x. And now from here, what we'll notice is that we have a pattern emerging, because if we look at the coefficient of x here, in each of these, the coefficient is 0 here, and here the coefficient is 1, and here the coefficient is 4, and here the coefficient is 13. So we now have a new sequence, and if we are able to find out what this sequence is and what the formula is, then we can plug it into here and easily find the general formula for all sequences. Now, the best way to do this is to notice that if we multiply each of these terms by 2, we can get 0, 2, 8, 26, and take half of these to maintain the original. And what you'll half, and then this is 3 to the n minus 1, because the terms of 3 to the n minus 1 would be 0, 2, 8, 26, and so on. So now that we have this, we now have this formula for these numbers which appeared here. And in this case, we said that r is 3. Now, I'd like to rewrite this a little bit, and let's say that I'm going to rewrite this as 3 to the n minus 1, but what I want to do is I want to rewrite the bottom in terms of our common ratio between the differences. So I'll divide it by 3 minus 1. Okay, so this is just one example. Let's try another example and see if it follows a very similar pattern. So let's try it again. So let's say I have another set of terms in a sequence, and let's say that the difference between the first two is x again. But this time, I'm going to say that the common ratio is 4. Between differences is 4. So now, the difference between these two is 4x, and the difference between these two is 16x. And now, again, I'm going to rewrite all of these terms in terms of the first term, so this is what I'll get. Okay, and again, the coefficient of x, we want to see if we can capture what is the sequence emerging. And to do this, let's just write down the coefficients each time. Here, it's 0. Here, it's 1. Here, it's 5. And here, it's 21. And let's do a very similar thing in this case. So, in this case, we want to see, like, what is this representative of? So, to get this sequence, we can multiply each of these terms by 3, and then you'll get 0, 3, 15, 63. And we're going to take a third of this because we want to maintain the original. And now, looking at 0, 3, 15, 63, we can now notice that there is a pretty clear pattern happening here, and it's very similar, because in this case, the general formula for this sequence would be 4 to the n minus 1, because the terms of this would go 0, 3, 15, 63. And knowing this, let's go back to here. Now that means that we have 1/3 of 4 to the n minus 1. And again, our common ratio between the differences is 4 in this case. So let's rewrite everything in terms of this common ratio between the differences of 4. So that would look like 4 to the n minus 1. And now we're going to do 4 minus 1. And I want to take a look at what's happening here. So if we take a look at what we have here and what we have over here, we can see that in both cases, we're doing the common ratio to the n minus 1 divided by the common ratio of the differences minus 1. So we can say that this is r to the n minus 1 divided by r minus 1, as what is happening is the coefficient for the x for every one of these sequences. So now that we have this, let's go back to our original. And now that we have this, let's now rewrite each of these in terms of this coefficient. So now we'll have a0 plus r to the n minus 1 over r minus 1, and then times x, and then a0 plus x times r to the n minus 1 over r minus 1, and every one of these terms is going to be, oh, and even the first term will follow this as well, because this accounts for all coefficients of x. So we'll have this. And now every single term of the sequence following is now following this one pattern here, which is a0 plus x times r to the n minus 1 divided by r minus 1. So this is the general formula for the sequence. And now to make it a little bit more clear of what's going on, we can reorder this a little bit. And when we reorder this, we'll see that this can be rewritten as this. And this is the same thing. And now I want to identify or make clear is that this here is the scaling, and I'll explain what this means in a moment. And this here is the shift. Now when we had a normal sequence like a to the a sub n as a geometric sequence, like 1, 3, 9, 27, we also had this occurring right before us. And in this case, the common ratio between the differences is 3, which isn't surprising because that's just the common ratio as well. But all that's happening here is that we've just been scaling it for the geometric sequences. But for this sequence here, this accounts for all cases of scaling and shifting, and all transformations. So ultimately, this is the general formula. Thank you for watching.